The calculus is arguably the most powerful technique in mathematics. Its two central problems are easy to state. First, the gradient problem, to find the gradient of a curve at any point on the curve. The second problem is the area problem, to find the area under the curve. A solution to both these problems was invented in Europe in the 17th century, but the process of invention was far from simple. It involved mathematicians from several countries, notably France, England and Germany, and resulted in a huge controversy about who got there first.
Pierre Fermat was a magistrate in southern France and an amateur mathematician.
Isaac Newton is the English inventor of the calculus.
Leibniz was a multifaceted person, but above all, I'm impressed by the fact that he exchanged letters with more than 1,000 correspondents.
Pierre Fermat, Isaac Newton, Gottfried Leibniz. Each has at some time been credited with the invention of calculus. None of them saw calculus in quite the way it's seen today, but each played a key role in its birth. Our story starts in the early 17th century, when France was the centre of the mathematical world. Jean Pfeiffer is an historian from the Centre Alexandre Coiré in Paris. Jean, can you tell me about the French mathematicians at this time?
We have first René Descartes, who was an important mathematician and philosopher who was trained by the Jesuits in La Flèche. He had a private income, so he could travel around Europe. He served in the army in Holland and in Germany. And from 1628 on, he settled in Holland, where he invented analytic geometry. For Descartes, mathematics was only part of a larger program, the task to put together a body of reliable knowledge. And one way to have reliable knowledge is to have reliable means to solve problems. For instance, in mathematics, if you have to solve problems, you should use coordinates, algebra, equations, and so on.
So did Descartes actually solve the gradient and area problems?
No, he did not really solve it, but he contributed a lot to him. He paved the way by creating his analytic geometry. But there was another man waiting in the wings, the lawyer Pierre de Fermat, down in Toulouse, who had a great passion for mathematics and made huge contributions to it. In 1629, at the same time as Descartes, he began to apply analytic geometry to the problem of finding maximum and minimum points on curves.
Jean took me through some of Fermat's ideas for finding maximum and minimum points.
Oh, let me show you. Fermat presented an algorithm, a mechanical procedure, without no justification. So we look at an example which Fermat also presented. Here you have a curve, y equal to x squared minus x cubed. And that curve may have a maximum at x. X plus a then is a nearby value. Then the two values of the y's here are nearly equal, as you can see on the picture. So Fermat is putting the two expressions equal to each other. So we have this equation here. Then Fermat is doing some manipulation, and at some point he is neglecting all the terms in a, because a is infinitely small. And so he gets this equation and the result. You have a maximum if x equal 4/3.
So could Fermat also find tangents?
Oh, I will show you again an example. Fermat considers a parabola, which is here, with an axis horizontal. And he wants to construct a tangent to the parabola at point B, which is here. In the Euclidean way of constructing straight lines, you need a second point. So Fermat is trying to find the intersection E with the horizontal axis. So he has to find the length EC. Now what does he do? He considers a second point F on the tangent, which is very close to B and which is also very close to the parabola here. The distance between the tangent and the parabola is very small. So again, Fermat can adequate the two values for y Then he does some manipulation again, and he can apply exactly the same algorithm we saw before. And he will find the answer that the subtangent EC is twice the length of DC in the case of the parabola.
So he knew how to find tangents?
Yes, but he also developed a remarkable method of calculating the area under the curve y equal x to the n. Here is dividing the x-axis by a certain number of points, x, e squared x, and so on, e being less than 1. Then he's constructing rectangles on these points, x, ex, and so on, and he can calculate the areas of these rectangles. The areas of all these rectangles form an infinite geometric sequence, and Fermat was able to calculate that sum. Then he sets E equal to 1, and all these rectangles are infinitely thin. And the sum of these infinitely thin rectangles is then equal to x to the n plus 1 over n plus 1.
Did Fermat make any connection between the gradient problem and the area problem?
No, he couldn't really do so because he was asking geometrical questions. He was looking for a construction of the tangent on the one hand and constructing an area on the other hand. To construct the tangent, he had to search for a second point to be able to trace the line, and to construct the area under the curve, he constructed a sequence of rectangles. So even if his methods are algebraic, the questions he asked were geometric, so he couldn't really make the connection.
Did Fermat communicate his discovery to others?
Yes, he sent his results to Mersenne, a friar in Paris, who circulated his results among the mathematical community. In particular, Mersenne told Descartes about Fermat's methods. Descartes was very, very critical about, but finally accepted the methods of Fermat. Fermat also wrote to Wallis in England, and he asked Wallis very, very hard questions on number theory to test his knowledge in mathematics.
John Wallis was a very accomplished mathematician and an expert on many subjects, including codes and ciphers. Open University maths historian Jeremy Gray.
Wallis was a professor of mathematics at Oxford. He wrote a book on conics, and then, in 1655, he wrote a book called Arithmetica Infinitorum, the Arithmetic of Infinites. And in this book, he did several key things. He had the formula for the area under y equals x to the n that Fermat had for various values of n, of course from 0 to 1. He invented the lazy 8 symbol for infinity that we use, and he invented and made systematic use of a notation for fractional powers of x.
Wallis's book had a great influence on one of the creators of calculus, Isaac Newton. Newton was born in 1642, more than a decade after Fermat had discovered how to find areas and gradients. He came to study here, at Trinity College, Cambridge, in 1661. Newton soon began studying the works of leading mathematicians, including Descartes and the Dutchman Christian Huygens. Lectures by Isaac Barrow, the professor of mathematics here at that time, taught Newton about optics and Fermat's methods of finding gradients. But life in 17th century England was sometimes precarious. 1665 to 1666 was the time of the Great Plague in England, and Trinity College was closed. So Newton returned home to Lincolnshire, which proved to be his most productive time, because it was there he made a remarkable discovery about the binomial theorem and linked this to both the area and gradient problems.
Newton studied Wallis's book on the arithmetic of infinites, and this led him to a novel idea, expressing answers to problems as infinite series in powers of x. Wallis had wanted to find the area under this curve with the equation y equals 1 minus x squared to the half, all the way from x equals 0 to x equals 1. Newton found he could do much better. He could find the area from x equals 0 to any value of x, say this one. He expressed the answer as an infinite series in powers of x, which is a remarkable thing to do. At first, his methods were rather like those of Wallace's, actually clever guesswork. But he soon found he could make systematic sense of the infinite series that arose, and in this way he discovered the general binomial theorem. The form of the binomial theorem had been known for a long time for integer values of n. You get an expression like this: finite number of terms, the value of n goes down by 1 each time, and the number of terms in the denominator goes up by 1 each time. What Newton discovered was a different expression for arbitrary values of exponent, for example, a half here. You still find that the exponent goes down by 1 each time, that the number of factorial terms, the terms in the bottom, increase by 1 each time, but now the whole expression is infinite. It never stops.
So why are fractional powers so important?
Well, Newton used his method of infinite series to solve area and gradient problems for all sorts of curves, including curves with fractional exponents. In the course of doing this work, he discovered something very important. If you take a curve like this with a fractional exponent, like y equals x to the half, Newton found that he could investigate the area under this curve from 0 to any value of x, and he found in this case that it was 2/3 x to the 3/2. And now, because he was happy with fractional exponents, he found that he could investigate the rate of change of the area curve, and he found that the rate of change of the area curve at x was equal to the height of the original curve, y equals x to the half. So he had a way of going from area problems to gradient problems and back. And this is what we call the fundamental theorem of the calculus.
So in effect, Newton found areas by looking at rates of change.
Oh, absolutely. And that's very important because finding areas is difficult and finding rates of change is easy. So Newton could solve hard problems, area problems, by finding that they were solutions to other problems, easy problems, that were gradient problems.
So how were Newton's results recorded?
Well, there was quite a lot of secrecy, but Newton did communicate his results to friends, and in 1676 he even wrote a letter to Leibniz, a long letter describing what he'd done. But the key results that he'd found he only gave in the form of acronyms, 40-letter acronyms, which obviously didn't tell Leibniz anything. And actually that's the point, because what Newton is doing then is signalling that he's got priority in these discoveries without letting on what they are. Then a bit later, Wallace started to circulate some of the things that Newton had discovered. And then finally, of course, in 1687, Newton really does publish. He published his great book, the Principia Mathematica, which is the book that applies geometry to the study of the solar system and lots of other topics in applied mathematics. So now Newton was thinking in terms of fluxions and fluents for the calculus, and in this book, in fact, he'd moved on from fluxions and fluents to first and last ratios, which is a limit concept, much like we have in the calculus to this day. But actually, the Principia isn't written in the language of the calculus. There's little bits of calculus in it. It's really a geometry book.
Unfortunately, Newton's writing was full of difficult concepts. He also used a rather specialised notation. However, a clearer version of these new ideas emerged from elsewhere in Europe. Niels Janker is a maths historian from the University of Essen in Germany. So can you tell us a little bit about Leibniz's background?
Well, he was born in 1646 and he went to the University of Leipzig in 1661. He was talented in many areas, in philosophy, theology, languages, law, and mathematics. And at the age of 20, he was offered a professorship at the University of Altdorf, but he refused it and preferred to become a diplomat.
And what got him interested in these problems in the first place?
Well, it was in a diplomatic mission when he came to Paris in 1672, and in Paris he met Christian Huygens, and Huygens was a famous physicist of his time and also a very, very good mathematician, and Leibniz was eager to learn mathematics from him, and so Huygens posed him problems and he recommended him works he should study by other mathematicians, among them, above all, the works of Pascal. And then, after hard work, in 1675, he devised his own algorithm for determining tangents to curves, and he got the insight in the inverse nature between this problem of determining tangents and the problem of the area under a curve.
Niels explained Leibniz's insight to me.
He built a rectilinear model for analyzing curved lines. So he considered every curved line as a polygon with infinitely many sides, which are infinitely small. So look, for instance, here we have 2 points, and we connect these 2 points by a line segment. And this line segment is infinitely small. And then, okay, we have here the y-coordinate of the 2 points, and we get here the x-coordinates. And now we can say where the tangent is. A tangent line is simply an extension of this infinitely small segment. So we have here this tangent line. And Leibniz, as others at the time, called this from here to here as a subtangent. And so we have here the ordinate and the x-coordinate. And then for this second point, we have another y-coordinate and x-coordinate. And the difference between these two ordinates is the difference dy. And the difference between the two x-coordinates is the difference dx. So in fact, these are really differences. And now it's completely easy to determine the tangent line. There are 2 triangles here which are similar, this infinitely small triangle and this finite triangle up here. And so we have the proportion dy by dx is equal to y by t.
And Niels, what about the area under the curve?
Yes, for this problem of the area under the curve, he again applied his rectilinear model. So we have this sequence of points on the curve, infinitely many points, and we have all these coordinates. And then we introduce a function z, a quantity z, and z designates the area under the curve. And what Leibniz does is to calculate the difference of this z. So we have here the x-coordinate x and the y-coordinate. And the differential is the difference between the area between the origin and this point minus the area between the origin and this point. And so the differential is a shaded strip. And we have here the difference between these two coordinates is dx, and up here we have dy. And dz is exactly this difference between the two areas, exactly this shaded strip. And we can calculate this as dz is equal to y times dx. But by writing this equation, we have neglected this infinitely small triangle up here. But it can be easily shown that it is really infinitely smaller than this rectangle made up of y and dx. So this is correct within this calculus. And now we take the sum over all this dz, and this gives the area. So the sum is simply our z, and this is equal to the sum over all y times dx. And this integral sign here, as we are used to, is derived from the normal s. And so we have derived the fundamental theorem.
Leibniz invented the integral sign that's still used today. It's a long stretched S because he saw the process as summing.
And in fact, he invented also this letter D for the process of taking differences, differentiation. From this comes the name differential calculus. And in fact, this notation made it very easy to calculate. And so very fast he arrived at rules for differentiation, for instance, the product rule and the quotient rule. And at the same time, he had some communication with Newton, and they exchanged their results, and they realized that they both were able to derive series for sine, for logarithm, and other similar results. But Leibniz was very much aware that it was important to publish his results. And therefore he published his account to the differential calculus in a paper in 1684 in the Acta Eruditorum. This was a journal he had founded together with others some years ago. And he continued publishing other papers in this journal in the years to follow.
This set the scene for a bitter and pointless dispute between the supporters of Newton and the supporters of Leibniz as to who invented calculus first. As we have seen, both were leading figures in the creation of calculus as a powerful working theory, but they were by no means the only contributors. Descartes, Fermat, Wallis, Barrow and Pascal all played key roles.
It was a truly international effort which was started by Descartes and Fermat at the beginning of the 17th century. It was developed in later centuries by other French mathematicians.
And we haven't even mentioned the work of James Gregory yet. He was a Scottish mathematician, and in 1668 he published some work which was quite similar to the things that Newton and Leibniz were discovering, and he was in Italy at the time. But his work was even harder to read and wasn't much appreciated in his lifetime, I'm afraid.
The Newton-Leibniz dispute became more and more acrimonious and contributed to a growing divide between mathematicians in Britain and those in Europe.
The dy by dx notation wasn't used in England until the 1820s, and only after a campaign which involved Charles Babbage, the inventor of the calculating engine, finally it was introduced into English mathematics.
And by then, long after the deaths of Newton and Leibniz, yet another notation had been developed, back where our story began, in France.
By the early 19th century, a new notation was introduced by Lagrange in Paris, which was again the center of the mathematical universe. Lagrange called the gradient derivative of f and noted it f-x. Today, the two notations dy by dx and f-x are used almost interchangeably.
The result of all these new ideas is today's calculus. So, if we want to find the gradient of a curve at any point on the curve, we use the derivative notation f dashed of x or dy by dx, and in many cases there are standard formulas. Also, if I want to find the area under a curve, this time you use Leibniz's long S, the integral notation, and again there are many standard formulas. The remarkable thing about this is that these two are actually related. In fact, to find the area formula, I work backwards from the gradient formula. And this is what Leibniz and Newton discovered.
There's a bit in the Principia that I very much like, right at the end of the preface, where Newton says, "And I heartily beg that what I have done may be read with forbearance, and that my labours, in a subject so difficult, may be examined, not so much with a view to censure, as to remedy their defects."